Hello, my name is David Watkins. I am representing the Kerg Lab at Columbia University. This work was done in collaboration with Rascal UC Davis and the Department of Rehabilitation and Regenerative Medicine at the Columbia Medical Campus. This work describes a new human-in-the-loop assistive grasping system for individuals with varying levels of physical capabilities. We investigated the feasibility of using 4 potential input devices with our assistive grasping system interface, using able-bodied individuals to define a set of quantitative metrics that could be used to assess an assistive grasping system. We then took these measurements and created a generalized benchmark for evaluating the effectiveness of any arbitrary input device into a human-in-the-loop grasping system. For our experiments, we used a Kinova Miko arm, which has 7 degrees of freedom and a parallel jaw gripper to pick up a series of different sized blocks as well as an arbitrary object from the YCB object database. The 4 input devices were a mouse featuring 2 buttons displayed on the screen presented to a user. The 2 buttons were cycle and select, which would allow a user to cycle through the choices displayed on the screen and also select an option and execute that command. A speech recognition device, in particular an Amazon Echo, which would respond to commands that were present on the screen. This would allow a user to input commands such as rerun vision organically as displayed on the screen rather than using a cycle and select paradigm. Echo. Tell robot rerun vision.
Successfully sent rerun vision to the Miko.
They were able to use an assistive switch, in particular the ultimate switch number 1671, which is a toggle switch that features only 10 grams of force to activate. Users could press and release the switch to execute commands, and by varying the length they held onto the switch, they could input either a cycle or a select into the interface. We designed a simple and easy to understand graphical user interface for the ultimate switch that allowed the user to easily understand what commands were going to be executed into the system. Finally, users used a novel SEMG device developed by our group that was connected either to the forearm or behind the ear of the subject. Users would provide input into the system by varying the intensity of the flexing of muscles underneath the sensor. For example, a medium flex would cycle options presented on the screen, whereas a high flex would select the option present on the screen. This would allow them to use muscles on their body as opposed to using full arm movement, which may be difficult for some severely disabled persons. We had 15 different subjects come through our study, each compensated for their time, and each of them provided input into the system, first by moving 3 blocks, followed by moving 1 arbitrary object from the YCB object database. They had to perform this task for each of the 4 input devices previously mentioned. These preliminary results provided insight into how different interface devices performed for generalized assistive grasping tasks, and also highlight the potential of SEMG-based control for severely disabled individuals. We found that all 4 input devices took roughly the same amount of time to input commands, and the grasps took roughly the same amount of time to execute for every single object. Users were successful 100% of the time when picking up cubes of varying sizes, and successful 76.5% of the time when picking up arbitrary objects.